Thank you, Ben. Uh, I appreciate you inviting me to this open science talk. Um, I okay. So in this talk today, I will be talking about all of us probably are aware of nowadays that what is nanomaterial, and then it is actually nanomaterials. People are making it since ancient days, but the science of these came up probably 1980s. From that time onwards, a lot of advancement has happened, including the synthesis of these nanomaterials, making different heterostructures. I'll be explaining what these heterostructures are, and along with this synthesis of these new materials, which shows very exotic properties and very exciting properties, um, it also demands that what is actually happening inside that nanomaterial, of how the structures are forming. These are also important. These are becoming important to know. So, in this talk, I will be talking about internal heterostructures, and it's primarily I'll be talking about photoelectron spectroscopy, which is otherwise very surprising that how photoelectron spectroscopy can be used, something to know about internal heterostructures, whereas primarily photoelectron spectroscopy is known to determine the electronic structure of the materials. Okay, good. So, as been introduced, I am Pralay. I work as a scientist at Center for Nano and Soft Matter Sciences in Bengaluru, India. So, I did my bachelor's from St. Xavier's College in Kolkata, in India, and I did my master's and as well as my PhD from Indian Institute of Science in Bangalore, and followed by I was at University of Notre Dame. That's where I met Ben first, and then I worked 2.5 years at Stanford University Chemical Engineering. And before joining this center, I was 1 year at Uppsala University. So my work all throughout was primarily focused on quantum dots and various aspects. Okay, good. So currently, since last 2000, end of 2016, I started my group here. We focus on understanding new materials, which are primarily relevant for photovoltaics. And now we started also looking for other applications of these materials. We use a lot of synchrotron techniques to understand these materials, and we also work on sensors, and recently we started developing with thin flames with precise control in thickness, basically atomic layer controlled thickness by a technique called atomic layer deposition. So today primarily I'll be talking about this heterostructure of inorganic perovskites. Before going to the main topic, first this is my group, although it's a 6 months old picture, but the student who will be who has primarily done the last part of work is Anamol Hawk, this the student over here. Yes, done this. Okay, good. So all of us know that nanometer is 1 into 10^9 meter. And sometimes these large numbers, what we do not deal with every day, we do not get a feel. So we know that if I look for a hair is something which you can feel it, a thickness of a hair. And roughly one hair thickness is around 100 micrometer. And 100 micrometer, that is nothing but 100,000 nanometer. So that means if we take a hair and if we chop it into this 100,000 pieces, then one size of it is 1 nanometer. See, when we deal with this is such a small number we are talking about, and the when we take this material, say if we take a gold, okay, the gold ring, it looks very different when we take it to such small sizes. And a lot of not only gold, there are several other materials, particularly semiconductors, they change a lot of their electronic properties. So how do we see this material? We basically seeing is believing, as this is very small, so we need to we know that seeing is believing. There are two techniques basically, primarily a direct way to see this and indirect way to see this material. Okay, in direct way we talk about, say for example, transmission electron microscopy. Yeah, all of us probably know that, say here, instead of the photons, so instead we use electrons to see this material. And of course the high resolution TEM are there, and say for example another technique, STM is there. So these are the carbon atoms on highly oriented pyrolytic graphite, or other is known as HOPG. And there are of course several other techniques like AFM, ACM to some extent. We also see these materials. And there are certainly indirect ways like, say, diffraction, where we look at the peak width, then other scattering techniques. Or say, for example, dynamic light scattering. There also we see the material in indirect way. Okay, good. So this is a picture of, you see that nanocrystals. Here, these are, I'll tell about this. These are this perovskite cesium lead bromide, CSPB BR3 nanocrystals. Okay. Now here, I want to point out, see, for example, if I look at this, this nanocrystal, here you see that the atomic planes, whatever these lines we are seeing, they are perpendicular to this edge. Okay. Now come to this nanoparticle. Here in this case we see this the same atomic lines, they are 45-degree angle with respect to the edge. Now the question comes, are they going to have this different property, or why is it forming that one is perpendicular, one is with 45-degree angle, and we see so many variations. So it is important, even if we are synthesizing this material, it is also important to understand this type of things, why they are happening, so that we can advance this field overall knowledge, and we can apply this for proper applications. Okay, so how do we make nanocrystals? We know that it is very small. So what we can do is that we can take a big solid and then start chipping it. So grind it till it becomes so finely divided that each piece is in the nanometric region. Correct. So, but this is some technique people of course use it, particularly ceramics, and in in case of ceramics nanomaterial, people generally synthesize, and this method is called. That's why it's top-down method. So you were starting from the big, and then you were going down to smaller. And then there is another way, the chemist way, more as that bottom-up approach. So basically, you want to make a nanoparticle of, say, compound A and B, AB. Okay, excuse me. Yeah. So what we have to do, that when we are forming AB, that means we need some A plus and B minus. Now, if we go to the market or or any chemical store, then they can't give A plus. So A always comes with the salt of A, and B will also come with some salt of B. So this, if we take and salt of A and salt of B, and then if we add them together, then what happens that it generally forms the bulk compound. Bulk means these are not generally in the nanometric size, because that is the thermodynamically stable state. So one need to stop this reaction at some point when A plus and B minus are reacting to form this AB. Before it goes to the bulk, we have to stabilize this with help of some passivating molecules. So basically, when AB is growing, then some other molecules, they come, these passivating molecules, and then they stop the growth, and thus AB nanoparticle forms. I'll give a small example here. Say, for example, lead sulfide quantum dots. These lead sulfide quantum dots are used in various applications like photovoltaics. I think lead sulfide based photovoltaics have now efficiency around 11 or 12%. And then, of course, lead sulfide is widely used for photodetectors. So to synthesize lead sulfide, so this is PB and this is S, A and B. So we need some salt of A. So that's what we have taken, lead oxide, and sulfur salt is this sulfur. So trimethyl dicyl. So it's bis trimethyl silyl sulfide. Okay. Now this reaction, we need to, in the reaction we need to get Pb2 plus and S2 minus. This compound easily breaks. It does not have any issues. This is a highly reactive compound, the sulfur precursor. Whereas lead is not, lead oxide, it does not react immediately. So what we do, we take lead oxide, we add some acid, oleic acid, in a solvent which does not interact with any of them. Then what happens that at high temperature and under high vacuum, this lead oxide, it reacts with the acid group of this oleic acid. It forms lead olate. And the oxygen it forms as it reacts to form water, and as we are applying vacuum and high temperature, it goes away. The water removes from the system, from the reaction mixture. So once this lead olate forms, then we add this bis trimethyl silyl sulfide to form this lead sulfide. And you see here we are adding the oleic acid. This oleic acid also acts as a passivating ligand of this for this nanomaterial, lead sulfide. So it's like this brown coat, that is the lead sulfide, and on the surface we have these oleic acid molecules. Now you can easily understand, or at least intuitively guess, you can guess that depending upon the temperature, depending upon the concentration of these precursors, or even depending on the concentration of these passivating molecules, one can control the size of this nanocrystal. What is the final size of this? So these are the lead, each of these dots, whatever we are seeing in this case, those are the lead sulfide nanoparticle, which are only 3.2 nanometers in size. Okay, so what is special about nanomaterials, particularly in these cases? We know that particle in a one-dimensional box, where the electron or any particle basically kept inside a box which has a potential 0, and outside it has the potential is infinite, correct? So the particle cannot escape. Why we are giving this example? Because when we are talking about one individual nanoparticle, the electron in this system, it cannot escape as such from this material. So we can assume it is very similar, it is behaving very similar to the particle in a 3D box basically. Correct. And there we know that as we change, so if we talk about, say, this is the nth energy level, this is the n plus 1. So the difference between two energy levels, it is proportional to, inversely proportional to the L square, the length of this box. So what does it say? That as we change the dimension of this box, then this energy level difference will change. Correct? So if I translate the same thing towards these nanomaterials, to these semiconducting nanomaterials, or otherwise also known as quantum dots, then it tells that if I change the size of this nanoparticle or the quantum dot, then this interparticle, the inter-energy spacing, that is going to change. Right? So that means the electronic properties of these nanomaterials are changing, and that's how it plays a major role. It becomes interesting. These quantum dots become so interesting point to study. Again, this is the example. Say we are considering this is the size of the nanoparticle, and then this is the valence band, and this is the conduction band. So at 0 Kelvin, all the electrons are in the valence band. There is no electron in the conduction band. Somewhere in between, the Fermi level will be there. Now, if you decrease the size or if you increase the size, what will happen that this is what we are considering about two energy levels, which is if I draw similarity with respect to particle in a 1D box. As I have increased the size of this particle, then the interparticle, this interband energy, the valence band and the conduction band, which is known as the band gap, that will be decreasing. And if we make the particle smaller, then what we know that the particle, this band gap will go up. It will increase. So, and here I just want to give an example that, say, for example, we talked about the valence band and the conduction band. Now, if we shine some light which is higher than the band gap of this material, then what will happen? The electron in the valence band, that will absorb this photon. and it will go to the conduction band, correct? It will create a hole in the valence band. Depending upon the energy, it can go even higher at the energy level. Then it relaxes very fast to the conduction band, and as there are no more states available here, so then it recombines with the hole, and that time it gives a photon out. That's what the photoluminescence. So it's basically recombination of the electron and hole. Okay. So this is the photograph. These are the photographs of, sorry, photograph of cadmium sulfide nanoparticles of different sizes. All these are cadmium selenide nanocrystals, okay, in solution, dispersed in solution. Of course, we see their absorption is different, as well as when we shine with, say, UV light, the same nanocrystals, the color changes, correct? So we see from blue to red, we can tune over almost the entire visible range. And as the size is, in this case, the size is increasing from left to right, so the particle band gap is going down, and that's why we see the photoluminescence, or the PL, yeah, the photoluminescence, it shifts to the red. Okay, so there are of course different, not only on size, one can keep the size same and change the composition. This is selenium to sulfur. As we increase the selenium concentration, the particle goes towards the lower band gap, correct? Now, this is where the interesting point comes. So for example, so far in the previous case, we talked about just bare cadmium selenide. That means though everything is cadmium selenide, on the surface we have passivating ligand. Then the quantum yield, that is 10%. What is quantum yield? See, I am signing 100 photons to this material. I am exciting with 100 number of photons. And what I am getting is 10 number of photons coming out as photoluminescence. That is what the quantum yield. Okay. Now, the same cadmium selenide nanocrystal, if we passivate, if we form a core shell type of structure where the core is cadmium selenide and the shell is cadmium sulfide, and then we have the passivating ligand molecules, then we find that the quantum yield goes up to 50%. And now, another way to do the synthesis is that you take the cadmium, you inject sulfur and selenium together. Then what happens that selenium is more reactive to cadmium. They forms at the core cadmium selenide and gradually it transforms to cadmium sulfide. So this one, the second one, is a core cell type structure, whereas this one is a gradient alloy type structure. And there the quantum yield we find it goes up to 85%. Although all the materials are identical. So there must be there is basically, I'll give the answer right away why the photoluminescence efficiency goes up. Here what happens that you have a lot of defect states on the surface, and those defect states which acts as a non-bonding orbitals, if I consider with respect to molecular orbital theory, then these states, these non-bonding or the dangling bonds, these correspond to the surface states. Basically, they come in between the mid-band gap region. And the electron, once excited to the conduction band, they took that path and then they recombine non-radiatively. So as the photon is not coming out in the non-radiative process, so we get a very low quantum yield. In this case, we remove those surface states, so the quantum yield goes up. But still cadmium selenide and cadmium sulfide, they have different lattice spacing. So there is a lattice mismatch. That's why the efficiency still is not very high. But when you go to CDAC to CDS, as the lattice spacing is changing slowly, so the quantum yield is very high. We can get around 85%. And there are again some other type of structures. This one is quantum dot quantum well. What is quantum well? Basically, here you see that we are using the high band gap zinc sulfide, and then we are using cadmium selenide, and then again one shell of zinc sulfide. So high band gap, middle part is low band gap, and again high band gap. That is the structure of the quantum well. And as everything is inside a nano, so everything is a quantum dot nanoparticle. So people call it quantum dot quantum well. Now these are the structures which came up intuitively based on the understanding of the reactivity of this material. Now, it is also important to know what is actually happening. Why, when I am saying that this is a gradient alloy structure, how do you know that? So that is going to be the main part of this talk. Okay. Now, before I go move to the next part, I would just quickly want to mention that we have so far talked about this inorganic core, but we have this inorganic core as well as the organic passivating molecules, and this quantum dot and ligand. This quantum dot and ligand, they play a major role in controlling the overall the size distribution, the anisotropy, basically different type of, say in this case, the gold nanoparticle. This has a very broad size distribution, but when people add to this thiol at room temperature, it goes to monodisperse. So, and when they reflux it, then everything, the size distribution even goes down further. And this process is reproducible. Now, these are the tin sulfide nanoplatelets. Now, why these are forming as a platelet? This is entirely because of the role of these passivating molecules, whatever we talked about. And not only that, you can certainly you can make the nanoparticle, so nanoparticle soluble in polar solvent or non-polar solvent by changing these passivating molecules. Okay, good. So now I just briefly tell you that, okay, this is a little bit old reference where we see that the perovskite is 20%, but now the perovskite is basically nothing but ABX3. A is a cation, depending upon what is, say, let's say X is a halide ion, so AbX3 we are talking about. So A is a 2 plus 2 oxidation state cation, B is a plus 1 oxidation state. Yeah, sorry, A is plus 1, B is plus 2, and X is minus 1 oxidation state. So the efficiency at this moment, the perovskite solar cell efficiency is somewhere around 25%. But that is with the bulk material. Anyway, so the perovskite for these perovskites, organic halide perovskites, there are also possibility to form these nanocrystals. Okay, good. So this is one example. This one is from Luther from NREL. They published in 2017. The photovoltaic efficiency of this cesium lead iodide nanocrystal based solar cell, they're around 13.4%. I think 2016, the same group came up first reported the device with 10.77. So in this case, they are using cesium lead iodide. In this case, also using cesium lead iodide. Why it is enhancing the efficiency? In this, the reason here is that the surface, the passivating molecules, whatever they were present in the surface, they have modified it to make it a coupled quantum dot array and a high mobility. That's why the efficiency went up. So what I want to indicate, basically, that the surface, when we're changing these ligand molecules, the surface of these nanocrystals are changing. And that changes the overall property of the system. So we also need to know that what is actually happening in the surface as well as the core of these nanocrystals. Okay. So we synthesize these materials. These are very highly efficient. The quantum yield can go up to 90%. And the FWHM, the full width half maxima of this PL emission is very narrow. And these are the nanoparticles, the TM image of this nanoparticles. Now people have done XRD. We have done X-ray diffraction to know what is the crystal structure, and we find they are kind of in the orthorhombic crystal structure. It is orthorhombic because this structure is basically, this one is the lead, and this is 6 coordinated octahedral environment with bromide, 6 bromide, and these PB bear 6 units. They are, because of their particular size, they are slightly tilted. So if it was not this tilted, it would have been a straight one. But here we see that they are tilted. That's why it goes to it's in the orthorhombic crystal structure. Now, if we take this material, this nanocrystal dispersion, Okay, and if we add excess oleic acid, we see that from the transparent colored solution, it goes to some hazy solution. Now, if we add to this one excess oleic acid, olyl amine, then it becomes colorless. And in this case, when we add excess olyl amine, again it comes back. Whereas if we add excess olyl amine or oleic acid, passivating molecule, we are talking about, these are the passivating molecules, then we find that there is no change. Right? And from dynamic light scattering, we have shown that when we add excess oleic acid to this material, then the average size goes up. Here, what it is actually happening, that the particles started agglomerating. So I want to bring out the point that the surface, how these passivating molecules are interacting with the surface of the nanocrystals, that controls the overall property. Okay, so we have to understand that how this surface, or what is actually happening at the surface. So, well, we did NMR in 2D NMR. Let's not go into the details. What we found here is that the oleic acid is present in the system, but it is not bound to this nanocrystal. Whereas this amine group, it is bound to the surface of this nanoparticle. That is what we understood from this NMR data. Okay, good. So what is actually the internal structure inside this particle, and also the surface of these nanocrystals? So to understand this, we use this variable energy X-ray photoelectron spectroscopy. So photoelectron spectroscopy, what happens that you shine a certain energy photon, and the photoelectrons, when they generate the photoelectrons, and then if they have sufficient energy, then they will come out from the material. Now, when they come out, say for example, a photoelectron. This is I am showing it's a material. Now the photon is generating the photoelectron is generating somewhere here. Then what will happen? It has to come out through this lattice, correct? So this electron is going to collide with other atoms inside the system, or other electrons, and those are going to be, there are possibilities of elastic scattering where they will retain the energy, and also inelastic scattering. In case of inelastic scattering, it will lose the energy. So we'll see it at much lower kinetic energy. Now that is defined. So the mean free path, that is the mean distance between two elastic collision, is known as the mean free path. Okay. Now the mean free path of the photoelectron, it depends on the kinetic energy of that photoelectron. Now, from the photoelectric effect equation, where h nu equals to binding energy plus kinetic energy plus work function, I should have actually written this equation. But anyway, so if we change the binding energy of a electron, of a particular material, of a particular electron, if we're talking about particular core level, they are constant, correct? Well, the changes with respect to the oxidation state, but otherwise in a given material, they're constant. So my binding energy is constant. And the kinetic energy, to tune the kinetic energy, what I have to do is to tune the photon energy, because the work function for a material is also constant. So as we are tuning the photon energy, we will be increasing the mean free path of the electron, and that indicates that the electrons, as we increase the photon energy, the electrons will come more deeper from the surface. Okay. Now, say in this material, whatever layered structure I have shown, say on the surface I have primarily this blue color material, and underneath I have deep down I have the red color material. So at lower photon energy, what will happen? I'll see that. So this is the one. At lower photon energy, I'll see very low intensity signal from this red color material. Okay, as we keep on increasing the photon energy, the more electrons will start coming out from more depth from the surface, so that the intensity will go up. Now here, this mean free path of the photoelectron, the average mean free path of the photoelectron, it is in the order of, it can be varied in the order of, say, a few angstrom to 2-3 nanometer. So when we are talking about a nanoparticle which have a dimension of, say, 7, 8, or even 5 6 nanometer, 5, 6 nanometer, then the radius of this particle is half of it, so around 3 nanometer, 2.5 to 3 nanometer. And the mean free path is also, we are talking about, we can tune in that range. So our probe, here the probe is basically mean free path of this photoelectron. That is what we are varying. So that is equivalent to the size of this nanocrystal. So as they are matching in this case, so it becomes an ideal tool to determine the internal heterostructures of this system. I hope we understood this, and we are going to employ the same thing to understand the rest of the, I'll give several examples where we have determined these heterostructures. So this is the example of cesium lead bromide. Here we have shown the lead 4F core levels. Okay, this is lead 4F 7 by 7 by F 7 by 2, and this is D 5 by 2. And in these are the cesium 4D and bromine 3D core levels. Correct. Here you find that there are two types of bromine present. One which has the lower binding energy, that is for the core, that means the bromine is more core, present more inside, deeper from the surface, deeper. And the other one is at the surface bromine, which is of higher binding energy. Now, to determine the heterostructure, what we did is we did this XPS at different photon energy, starting from 650 eV to 4000 eV. Okay. Now, with respect to the cesium 4D signal, for cesium 4D, we have normalized with respect to cesium 4D, and then we plotted all this photoelectron spectroscopy data, the spectrum. What we find that the bromine 3D intensity with respect to cesium 4D goes up as we decrease the photon energy. And there is something called photoemission cross section. After that correction, we basically plotted what is the intensity ratio variation with respect to cesium and bromine 3D. What we find that at 4000 eV or up to, say, for example, 1100 eV, we find that the ratio is almost 1:3. And that is what we expect, because the composition is CS, PB, Br3. So we expect CS to Br will be 1:3. But when we are using very low photon energy, the bromine 3D signal intensity goes up. It tells that the surface of these nanocrystals, the cesium lead bromide, are highly rich with the bromine. Correct? So they are rich with the bromine, whereas it's not rich with lead, because cesium to lead ratio, which we expect to be 1, CS, PB, Br3. So CS to PB should be 1:1, and we find they are almost 1:1. Whereas this bromine is very rich in the surface. So we did other calculations in terms of understanding how it is possible. What we find in this case, that this olyle ammonium ion, it actually replaces some of the cesium from the surface. Okay, so now you see that if I talk about this particular surface, I have less amount of cesium. Correct, one cesium we have taken it out, the bromine is remained same, and by replacing the cesium with this olyle ammonium ion, there is an opportunity for this olyle amine to form this hydrogen bond, Br and H, to form two hydrogen bonds, compared to if it just attach on the surface. So in this way, so here what we have from photoelectron spectroscopy, we found that the surface of these nanocrystals are bromine rich, and later we understood from these calculations that it is the olyle ammonium ion, it is replacing the cesium to form this, by doing this, it is able to form this hydrogen bonding, which is stabilizing the system, and thus the surface is more of the bromine rich. Okay, so in this case, unlike the traditional 2,6 quantum dots, 2,6 semiconducting nanomaterials, that is what the example I was giving earlier of cadmium selenide, cadmium sulfide, etc. Cesium lead bromide, it does not have a very good control over size. Okay, however, the composition, so tuning the band gap, it is possible easily by tuning the basically composition, by tuning the composition. The other example, what I was giving of CdSES, there if you change the sulfur to selenium, the ratio, the band gap also changes. So in this material, in cesium lead bromide halide, the anion exchange is a preferred route over the cation exchange to control the band gap of this material. So I'll give an example here. So in this, first I'll explain. In this system here, in the round bottom flask, we have taken lead iodide solution. Okay, and through this syringe, we are going to introduce cesium lead bromide nanoparticles. Okay, I hope this will work. Just yeah. Okay, so this we started injecting. We'll be switching on the UV light. You see that this is blue, but when it comes and reacts with this lead iodide, it becomes orange. The reason is, but if we synthesize pure cesium lead iodide, that will be red. So in this case, what is happening that cesium lead bromide and iodide, both of them has formed a complex like compound like CSPB BRI3. Okay, so this is what I meant, CSPB BR of I3. So this is the cesium lead bromide, which we see as the green color. When we add certain amount of controlled amount of lead iodide, then we form CSPB BRI3. And if we add excess lead iodide, then we form CSPB I3. And these we have probed from X-ray diffraction as well as, and from the TM also we find that the size slightly goes up when it converts to cesium lead iodide. And that happens because iodide ion is bigger in atomic, atomic radii of iodide is bigger. So if we consider the same number of anions present, then automatically the interplanar spacing will go up as well as the lattice constant, and that finally increases the size of these nanocrystals. Okay, so here the question is that we start from this cesium lead bromide, correct? When we are adding this lead, when we are adding lead iodide to it, or the vice versa, then we know that it is forming cesium lead bromide iodide. Is it a homogeneous alloy like this, what I have shown, or is it taking path B where it is a gradient heterostructure like cesium lead bromide at the core and cesium lead iodide on the surface? And then if we add excess, then from here, it is directly converting to CGS PPI3, or is it like the whole thing is on the outside, it is becoming so cesium lead iodide, and eventually the core is still cesium lead bromide, and finally it will convert to all the anion will be replaced to form to cesium lead iodide. So this is the question we wanted to understand. Or to answer this question, whether it is following the path A followed by path C, or is it following path B and then followed by path D, we have to understand what is the internal structure, heterostructure of these nanocrystals. So what we did X-ray, the photoelectron spectroscopy, again variable energy photoelectron spectroscopy for this cesium lead bromide, and one of these composition where we see this orange color, and then we consider the final. So these are the three systems we took, and we did the variable energy photoelectron spectroscopy over there for this material. Here I show the example for cesium lead bromide iodide and cesium lead iodide, which is fully converted, and which this one on the left hand side, it's shown in figure A, that is partially converted, partial anion exchange. So what we expect in this case, so this is the cesium 4D signal, this is the bromine 3D, and this is iodine 3D, iodine 4D. Now, as we keep on increasing the photon energy, we go up from 3500 eV to 6000 eV, we find that the iodine 4D signal intensity is going down. Now, when we see in this case cesium lead iodide, there we find that as we are increasing the photon energy, we still see some amount of bromine, very small amount of bromine present into the system. But when we do the experiment at 3500 eV, we do not see any bromine. One will consider by looking at the spectra, it is very tough to say that there is any bromine present. But here we find it is present. So these are the different, so after correcting the photo emission cross section, these are the ratios we have found. And this is with respect to the lead. We find that metallic lead glow goes up in these cases. So instead of going to so here again, I'd say that as we find that as we are increasing the photon energy, the iodine 4D signal is going down. That means there are less amount of iodine present at the core of the nanoparticle in this case. So it is kind of forming this gradient structure, what I have shown here, instead of having a homogeneous alloy of bromine and iodine. If it was homogeneous, then we would not see any change in the basically in the bromine 3D and iodine 4D photoelectron XPS data. Okay, whereas in this case, we find still some bromine present, although people have earlier assumed that the conversion is complete, that it converts from cesium lead bromide to entirely to cesium lead iodide. But what we have shown that it really does not convert entirely to cesium lead bromide, cesium lead iodide. That the some amount of cesium lead bromide nanoparticle, some amount of cesium lead bromide is still present at the very core of this nanocrystal. Okay, so basically what we have seen that it follows basically instead of following path A and C, it follows path B and then path D1, and probably it never takes the path D2. It stops somewhere here. The entire anion exchange is probably not possible in these systems, at least at the temperature where we are doing this anion exchange. Okay, so in conclusion, I'll probably conclude here that in the first part, what we have seen that the passivating ligands, which is the olyl ammonium ion, basically replaces the cesium from the surface of the cesium lead halide system, and thus it stabilizes the system with the formation of this hydrogen bond. And oleic acid, it does not interact with the nanocrystal, but it helps somehow in the stabilization. And anion exchange, it forms a inhomogeneous alloy, that means in this side, and complete anion exchange does not replace all the native ions in the cross side. And so these are the understanding of this material from the understanding of the internal heterostructure of this material, and all these we have achieved from the photoelectron spectroscopy, which the whatever the conclusion we got from XPS, those are supported by other experiments like NMR and the photoluminescence, etc. So I think here I'll conclude. The second part of this work is primarily done by my PhD student Anamol, and I would like to thank my collaborators, Dr. Anshuman Nag from ISAR Pune and his student Vikas, and the funding came from our institute as well as India at DESI. Basically, they support for these synchrotron experiments. This photoelectron spectroscopy variable energy XPS were done at Petra in Hamburg, Germany. Thank you very much.
All right, thank you very much, Dr. Pralay. That was, as I figured it would be, a fantastic talk. The chat would like to thank you for your talk, and I'll go ahead and say, chat, if you have any additional questions, feel free to go ahead and get them in. But we do have one here from a user, ArcTech, who had a question about how this maybe could be used, and had this to say: can variable energy XPS be used for determination of thin film uniformity? The example that they gave was deposition of like mixed oxide films via CVD or ALD. Can you comment
exactly.
on that?
Yes, I will certainly. And I have not done yet any work on that, but there are in literature, there are several. Sorry, I'm passing through these slides.
Yeah.
I want to come to. Here, after this. Here. Okay. So, as he rightly pointed out, that it is absolutely possible to determine any heterostructure. Actually, I am aware of, actually I am part of one of these who are in magnetic memory material, cobalt based,
Mm-hmm.
cobalt, magnesium and tantalum based material, where we have figured out that there is certain amount of, there is of course these are layered structure. Okay, layered
Okay.
structure means different thin films are deposited one on top of each other.
Mm-hmm.
And how the magnesium diffuses in these systems, there is one PRB, I can send the reference sometime later. But
Yeah.
coming to the point, certainly yes, it is possible, but keep in mind that the thickness of this layer which we are going to probe, it should be within the mean free path of this of the photoelectron. If it is too thick, then we are not going to determine, we will not be able to seeing that. If the material is very thick, then we'll be seeing only the surface at certain thickness basically, and will not be seeing what is going on underneath. So ALD grown thin flames, they are generally under 10 nanometers, or it can be certainly more, but typically they are very thin, and those will be ideal for this any heterostructure to probe with variable energy XPS.
Okay. Interesting.
Yeah.
What's what's sort of the maximum depth that you can probe? Like the, or I guess the maximum depth range maybe.
See, it entirely depends on the photon energy. I'll give
Mm-hmm.
you an example. So the relation is actually, I hope I'll be able to write here. Um, so it's an empirical formula. The mean free path of the photoelectron lambda, which is equivalent to half square root of kinetic energy.
Mm-hmm.
Okay, and this lambda is expressed in Armstrong, and whereas this kinetic energy is expressed in electron volt.
Okay.
Okay. So now, if you say, for example, when I was talking about sulfur, if I talk about sulfur 2p, which has binding energy around 160 eV, around 160, and if I use aluminum K alpha, which is 1486 eV, okay. So if we do the maths, it will come somewhere around, the mean free path will come somewhere around 1.8 nanometer.
Okay.
So now if you see that if you increase this photon energy to much higher, it will subsequently go up, but it does not go up proportionally. It is inversely
Mm-hmm.
square root of that kinetic energy.
Okay.
So 3, 4, 5 nanometer, again, you have to look for sources which are providing very high photon energy.
Right.
Another problem what comes technically, that as you go in very high photon energy, the photo emission cross section goes down significantly.
Ah.
So generally, when people are doing XPS as ESCA to understand the oxidation state, what are the different oxidation state of a particular element present in a system,
Mm-hmm.
people use typically low energy, lower photon energy. Okay. So there is a trade-off. Generally, people do it somewhere. I have done experiments. In this case, up to 6,000 TeV is what we have done.
Okay.
Yeah.
Is there any risk of damage when you go to that
Uh,
high of an energy, or is it a pretty non-destructive technique?
this is generally a non-destructive technique. It does not damage this. Well, it is both yes and no, I would say.
Okay.
First, I'll explain no. If the material is stable, okay, then it is non-destructive because it's just takes the electrons out, okay.
Okay.
But say in this example, when we are talking about cesium lead bromide, or the bromide, particularly more of this bromide iodide system,
Mm-hmm.
this one, you see that we find some amount of metallic lead present into the system, right?
Sure.
So why this metallic lead, when X-ray is falling on this sample, somehow the lead is coming out as PB0, and it happens more with this alloyed system compared to the pure systems.
Interesting.
So yes, it is destructive in that way that it sometimes if the material is not stable, it will degrade.
Okay. That's interesting because I've done kind of I guess standard XPS where you just have a fixed photon energy, and you're basically scanning to see what's there, what the oxidation states are, like you talked about. but it's kind of a fixed depth basically. So
Yes,
this is an
that's
interesting technique.
actually before the synchrotron development. Now synchrotron has been developed a lot over our research, whatever in our research time itself. Correct. We are only for maybe a decade, a little bit more.
Mm-hmm.
But earlier, what people used to do that they will use the same photon energy, correct, in the lab sources, but then they keep on sputtering.
It's 9 o'clock.
Sorry, they keep on. Yeah, there was some alert. Anyway,
okay.
so they keep on using sputtering. So you are doing XPS, then after you got the data from the, so which is surface sensitive, you use argon sputtering, and then you take out some sample from the surface, and then you do again. So that was kind of a destructive method
Yeah.
to determine. But here, instead of doing this argon sputtering, taking the sample out, you are just changing the probe and thus doing this, thus probing this heterostructure.
Yeah, it's an interesting take on it.
Yeah.
How long does an experiment using, or how long does this take to sort of gather the amount of data that you need?
See, it depends on the one more advantage before answering to that point. One more advantage is that doing these experiments at synchrotron, that it has very high photon flux. So the signal to intensity ratio is much better.
Okay.
But as you said, that compared to lab source, these samples will degrade faster if they are prone to degradation because you are using much higher photon flux. Okay. Now again, it depends on the concentration of the sample, which core level you are choosing. But typically here all the XRD. So I'd say that, see, for example, this lead 4F, which I have shown in the figure A, they took around half an hour to get this quality data, only for this lead 4F core level, around half an hour.
Okay. So you have to choose. You had it took you half an hour just to get that section.
Yes, exactly.
Okay.
Exactly.
Okay.
Yeah.
Interesting.
Again, these are very high quality X-ray, XPS data.
Right.
So yes. Yeah.
Do you know what kind of?
Use lead 40,
Sorry.
if you choose lead 40, then probably the time will be different to get the same amount of same quality of data because the photo emission cross section will be different.
Right. Okay.
Yeah.
What's the how trying to think of the right way to word this. What are the detection levels for a particular element for this technique?
Okay. See, it's actually people have yeah. Okay. Yeah, I'm trying to think. Is there any direct way to answer it?
Do you have like a ballpark idea? Like let's say in approximately in atomic percent.
See, approximately atomic percent wise, I think 1 or 2%.
Okay.
More than that, maybe tough. Again, it depends on whether you are seeing a peak which is not. See, in this case, let me go to say for example, in this case, in figure B, bromine 3D 5x2 and 3D 3x2. Okay, if this peak is say somewhere as is overlapping with something else, we'll not be able to see it.
Okay.
Say for example, 3D 5x2 and 3D 3x2, the spin orbit splitting, the difference between these two, if they are very less, then they will be overlapping. You will see it's a broad peak, so there is a chance of missing it. Correct. But if their spin orbit splitting are different, say for example lead, where the peaks are much sharper, so it will be much easy to identify that.
Okay.
So as I said, that there is no straightforward answer, because what core level you are looking, that matters.
Mm-hmm.
What type of photon energy, that matters. So yeah,
Okay.
but I have probed material where I can see even 1%, up to 1%. Yeah.
That's interesting. Okay. One last question for me, and Chad, if you have
Sure.
any more you want to get in, go ahead and do that now. Um, in terms of the actual technique, are you able to look at things in liquid, or do you have to cast a film to get good results?
These all are done on thin films. So we
Thin
took
films.
the quantum dots, we deposited it. Okay. And also one needs to be very careful. See, I talked about what are the beauty of these things, correct? I have not talked about what are the pain
Yeah.
to go through this experiment. uh, the sample should not be charged. You have to make sure that there is no charging when you are doing
Oh,
this experiment. If it is charging, then the core level will change, the peaks you will get it broad, it is not going to be a meaningful experiment.
interesting.
Although people report it, but it is not meaningful. And then see, for example, a lot of people, apart from this analysis is nothing but we are analyzing the intensity ratio with
Mm-hmm.
respect to the photon energy, at different photon energy. And people use XPS data to quantify different elements, correct?
Mm-hmm.
Now, if you use, say, one core level, which is at, say, for example, 700 ev, another core level at 70 ev, okay,
Yeah.
these are way far apart. Okay, now you are using, the photon source is identical, but the detector are detecting at two different kinetic energy region, so they will have different transmission function.
Mm-hmm.
So that is going to matter. So it is always good to have the data, the peaks. You should choose the peak which are near to each other. The binding energy should be very similar.
Okay.
Okay. Another thing is that you are choosing, say, one s orbital and one f orbital. Now s orbital and f orbital, they will interact differently with this synchrotron light because they are polarized,
Sure.
correct? So that also one needs to consider. If one would like to have a very precise measurement, then they should also choose the similar type of orbitals. In this case,
Okay.
you will see that we have primarily chosen the d orbitals in all these cases.
Okay.
So that also sometimes is can be important, although that has minor effect, but one should consider that.
Yeah, it still could. Yes, you got to pay attention to it for sure.
Exactly.
That's interesting. That's not one thing. That's not something I would have thought about, but that makes a lot of sense.
Mm. Mm.
Oh, all right.
Yeah.
I don't know. Are there any more questions from chat? I'll wait just a second because there's a delay.
Yeah. Sure.
All right. I think that's going to be it. I don't think I have any more questions right now. And so with that, we will wrap up, and I will say thank you to Dr. Pralay Santra. Uh, Again, a wonderful colleague, and he gave a great talk. He is at the Center for Nano and Soft Matter Sciences. If this technique interested you, and I'm sure he would love to collaborate. Feel free to get in touch with him. And I'd like to thank everybody who came out tonight and who asked questions. This video or this talk and the Q&A will be uploaded to YouTube. I'll probably upload it later tonight. It takes a little bit of time for YouTube to process it, but certainly by tomorrow morning it will be available. And again, I'd like to say that if you're watching this and you would like to give a talk, please feel free to reach out and contact me. You can email me at meekins@sc.edu. That's MEEKINS @sc.edu. That's my email. You can find me on Twitter at meekinslab, MEEKINSLAB, all one word. Or you can feel free to drop into our Discord. I just put the link in the chat there. But yeah, this is a lot of fun. And it's a lot of fun to listen to all the different talks. And I hope you will all come back out and join me next week. And I think with that, we can call it a night. Once again, thank you to Dr. Pralay Santra.
Thank you, Ben. Have a good night. Thank you very much.
Thank you. Good night, everybody.
Okay. Take care. Bye-bye.